thank you very much, Ben, for the introduction. And I would also like to thank all the organizers, so Ben, David, Goran, and Anne, for this excellent conference and for making us feel very welcome here. And I think we can congratulate you already upon a very successful conference, independently on how this final talk goes. So let us take the opportunity to thank the organizers. And that also encourages me to deliver a better talk, yeah, when you clap at the beginning like that, yeah. So, all right, so my talk might appear a little bit more abstract than some of the very beautiful talks that we saw in this conference. And one of the reasons is that my framework will not necessarily be a Markovian framework. But let us hope that it will still be beautiful in a certain sense, in a different sense than the talks that we have seen already. So it's based on some joint works with Marie-Claire Kenneth from l'Université Paris-Cité and Peng Yuan, who is one of my PhD students at the University of Warwick. We will place ourselves indeed in a framework which can be seen as lying in between the discrete and the continuous time. So the discrete case will be a particular case of our framework. So we will be able maybe to connect also to some to the talk by David Hobson earlier on and the talk by Louis earlier on. So we saw many talks in this, many beautiful and interesting talks in this conference in the continuous time framework. So I'm not an enemy of the continuous time framework. I have myself some, oh, now it goes backwards. Yeah, so I myself have some contributions with quarters in the continuous time framework. Of course, we saw, yeah, illustrated in this conference that there are lots of beautiful connections between different fields in this framework, but also we saw that treating this framework requires some rather sophisticated results and tools from the theory of stochastic processes. And here, in our exposition, due to the framework that we introduced, we do not need any results from the theory of stochastic processes. Yeah, and so I said, so the title was nonlinear optimal stopping. So it's not the first time in the conference that we hear this expression. So Goran spoke about quadratic nonlinear optimal stopping. So here the nonlinearity will be in a different sense, right? So I was thinking, so in mathematics, usually in mathematics we somehow agree what linear is, yeah, what a linear function is, what a linear functional is, yeah, what a linear operator is. But when we go beyond the linearity, we can be nonlinear in many different ways, right? Let me just come back. I'm not very experienced with working with this object, yeah. So, all right, I'll try to do with my hands. Yeah. So already, so instead of assessing payoffs with the usual linear expectations and the usual linear conditional expectations, we'll be assessing them by operators like that. And the linear example of that is just the usual conditional expectation, knowing the information at time s. But in my framework, the nonlinear operators might depend, not necessarily, but might depend on two time indices. Yeah, in the case of the conditional expectation, we have, so if I take the conditional expectation knowing fs, I have dependence only on the time index s, that is the time of evaluation, the time of assessment. Here I might also have dependence on tau, that is the time at which the payoff falls. Yeah, and I will give you examples of operators like that, which we meet with in mathematical finance and stochastic control. One very well-known example are the so-called G evaluations induced by backward stochastic differential equations with ellipsis driver G, let's say. And another very well-known example in mathematical finance and also in the risk measurement literature are the so-called dynamic concave utilities. But in general, those operators will not necessarily be concave or convex. Yeah, so I will not be able to use some convex duality arguments. All right, so let us introduce now the framework. First, what are the agent stopping strategies? So, first, I will look at problems in finite time horizon. So I haven't yet treated the so clearly we see that it's my first time speaking in the Field Institute because I do not yet master this clicker. But if you invite me again, I promise I will have improved. Yeah. So finite time horizon. I think the problem will also be interesting in infinite time horizon when t is equal to plus infinity, but we haven't yet done that. So I have an underlying filtered probability space which satisfies the usual assumptions. And just for completeness, equalities and inequalities between random variables will be understood in the P almost sure sense. And then so we give ourselves those stopping opportunities modeled by those stopping times theta k's. And what we require on those stopping opportunities, yeah, on those stopping times theta k's, is that this sequence be non-decreasing in the almost sure sense. Because it's non-decreasing, it converges to something, yeah, for almost each omega, and we require it to converge to t. So we have those stopping opportunities. It's a magical board. When we push up, another picture appears. Yeah. So yeah, so we have those. Yeah, let us. So we have here the fixed terminal horizon, and here we have those. Yeah, and the place of those stopping opportunity, of course, depends on omega, and they converge to t. And you see already that on some states of nature, one might have infinitely many stopping opportunities. On some other states of nature, a finite number of stopping opportunities, and the number depends on omega, and where the stopping opportunities are depends on omega as well. So, and the agents, the agents can stop only at stopping times tau of this form. Yeah, where what are those sets AK and A bar? They form a partition of omega, and AK is F theta K measurable, and A bar is F capital T measurable. So in fact, what the agent chooses are those sets. Yeah, what will differ between my stopping strategies, my stopping strategy and yours will be the choice of those sets. Yeah. So and the set of all stopping times tau of this form, I will give it a name. It will be capital theta, and I will call it the set of Bermudan stopping strategies. But let us be careful. That's more general than the Bermudan exercise times in Bermudan options in mathematical finance. Yeah, let us see that on the next slide. So here I present some subcases in a decreasing level of generality, and in fact it's this fourth case which corresponds to the exercise strategies in Bermudan options in mathematical finance. So this was our general case. This is the framework of our paper. So I can have a further particular case in which so this is case 2, in which for almost all trajectory omega, I have a finite number of stopping opportunities between the maturity, but the number of stopping opportunities, this number n, depends on the state of nature. Yeah, and the stopping opportunities themselves, of course, depend on omega because the theta k depends on omega. I think that for the case of the talk by David Hobson and also Louis, so I think their situation was something like that, because their stopping opportunities, they were the jump times of Poisson process, right? So And then a further particular case of that is when this n in fact does not depend on the trajectory. So whatever, whether you're in a good state of the nature or in a bad state, you have, let's say, n equals to 10 stopping opportunity, and what depends on omega are just the stopping opportunities themselves. And then a further particular case is when I require those theta k in fact to be deterministic, and that's exactly the situation of the exercise times in Bermudian options, because in Bermudian options in the contract, the times where the buyer can exercise the option are predefined deterministic times, usually equally spaced, and I think usually by 3 months. Yeah, so and in my talk, I will consider this first case. Yeah, so now I have defined, now that I have defined the stopping strategies of the agents, yeah, what the agents can use to as stopping strategies, I have to define what a payoff is. And in fact, it is natural in this framework to define the payoff directly for stopping times of this form, right? Not, There is? Oh, you think I need it? Let me see. Yeah, all right. All right, yeah, if I need it, yeah, thanks very much. I will use it. Yeah, thank you. All right, so yeah, if I stop at tau, yeah, what do I get? I get the random variable psi tau. And what is this random variable? What does it have to satisfy? It has to be f tau measurable, right? And moreover, if I know that tau is equal to tau prime, psi tau should be equal to psi tau prime almost surely. Yeah. So for each tau, I have a random variable psi tau. So if tau varies, I have a family of random variables. And the family of random variables satisfying property 1 and 2 is known as an admissible family of random variables. That's a notion which goes back to those papers which were mentioned here as well by Anne, papers by Elker-Wee, Bismuth, etc. Yeah, and moreover, I will consider that, so we know my examples, the payoff random variables will be in LP. Yeah, and in the example of the conditional expectation, P is typically equal to 1. In the example of the G evaluation, P will be equal to 2. And in the example of the dynamic concave utility, P will be equal to plus infinity. So, yeah. And because the family is admissible, if I stop at tau, psi tau can be written in this form. Yeah. So now I have the stopping strategies, I have modeled the payoffs, and now I have to model how I assess the payoffs. So I introduce those rho as taus. So this slide and the next might appear indeed a little bit abstract, but what we can do first is just to check in our minds that for the usual conditional expectation, that is for the conditional expectation knowing Fs, yeah, so those properties are satisfied, yeah. Those properties are satisfied. Of course, as I mentioned, for the usual conditional expectation, I have just dependence on S, the time of evaluation, but not on the second index. So here, this admissibility property of the operator rho S tau is in fact satisfied in all the examples, but in this abstract framework, we have somehow to put it. Yeah, what is this then third knowledge preservation property? So here, you see tau is after S. So here is S, and eta in property 3 is Fs measurable. So I know my payoff eta at S, and I want to assess it at some subsequent time tau. And of course, if I know it at S, if I know eta at S, I know it also at subsequent times. And so you might ask me, so what, so it's rho tau. Yeah. Here in this writing, the first one is always the time of evaluation. The second one is the one at which the payoff is revealed. Yeah, and so you might ask me, so what happens then to the interest rate? Yeah, because what happens then to the interest rate? It seems in this picture that it's equal to 0, right? But in fact, the interest rate, as we will see in the example, it is it comes in this row. Yeah, it comes in this row. So the next property I think is clear. It's just the monotonicity of the operator rho s tau, and of course that's true for the conditional expectation. The time consistency here nu is just stopping time, a Bermudan stopping time in between s and tau, some intermediate, yeah, Bermudan stopping time. And this time consistency property is just a generalization of the Tower property of the conditional expectation. Yeah, it tells me that if I assess directly, so here is where the payoff is revealed. So if I assess directly from tau to s, so I will obtain here the assessment rho s tau aveta, and I will obtain the same assessment if I assess in two stages. First at nu, and then I reassess from time s perspective. So I think those properties are clear. So then we have some a little bit more technical properties. So this first one is what we call the generalized Z1 law. Let us first think about the conditional expectation. So please note here that A is Fs measurable, A is known at time s. So this is clearly true for the conditional expectation, because for the conditional expectation, if A is Fs measurable, I can put it inside of the conditional expectation and take it outside without changing anything. And in my framework, I have to generalize that if you wish to. I mean, it's good if I have this property, yeah. And then those properties 7 and 8, those are some sequential continuity properties. Yeah, the property 7 is just the two property of the operator rho s tau itself. Here I just approximate eta, the payoff eta from below by some sequence of payoffs eta n. And if that is sufficiently integrable, what I say in this property that I can interchange limit and the operator, provided I put the inequality in this direction, in the correct direction. Of course, this is true. Property 7 is true for the conditional expectation, and for the conditional expectation, more properties are true, right? Because if I have sufficient integrability, I have also monotone convergence, dominated convergence, etc. Yeah, not just for Fatu's lemma. And this property 8 might remind you something that Anne explained very well in the framework of her work on the first day of the conference. So in general, you know, and she explained very well. Let us think, for instance, of the case, the linear case, the case of the linear conditional expectations and the continuous time framework. Yeah, if we have, for instance, a progressively measurable process, right, continuous, left limited, sufficiently integrable, and we want to optimally stop it, we might not find an optimal stopping time. We require some, to find an optimal stopping time, we require some additional left upper semi-continuity assumption on the payoff process. Yeah, and that is true in continuous time, but that is true also in the case where you have infinitely many opportunities of stopping, even though they're countable. Yeah, but now, so if I assume that the psi has some left upper semi-continuity property, and if I have sufficient integrability, the conditional expectation follows this left upper semi-continuity property, right? It will not break it. But now I work with those abstract rows, so I have to ensure, I have to impose something on rho, I have to impose on it that it respects somehow this left upper semi-continuity, and this is this left upper semi-continuity property with respect to the terminal condition, but also the terminal time, right? And this property 8, I need to impose it just when I want to show that there exists an optimal stopping time in this framework. So then, so let us see some examples. So let us see some examples. We are more or less convinced that the conditional expectation is an example which fits into the framework. So let us see another one, the G evaluations. So what are those G evaluations? So we first have to recall what are the backward stochastic differential equations with a given Lipschitz driver G. So here the space, so here P is equal to 2. So the payoff lives in L2. So here, so S is before T. Yeah, we first define the backward stochastic differential equations for deterministic times, and then we extend them to stopping times. And so we know. So what is here? Let us recall. What is the input the input of this equation is eta and the Lipschitz driver G, and the output is a pair of adapted processes YZ. Yeah. So let us think. So let us think of a particular case. So if I take, so yeah, you see, so with this equation, let us recall in the backward as the equation, what is given is the terminal condition. Yeah, and I want to match the terminal condition eta at the terminal time small t, but in an adapted way. Yeah. So if I take g equals to 0, so even if you are not familiar with backward stochastic differential equations, I think you'll be able to give me a solution, because then it's very clear that if g is equal to 0, a candidate solution will be just the conditional expectation of eta knowing fs, because this term w here is a one-dimensional Brownian motion will disappear in conditional expectation. Yeah, this will be the candidate solution, and in fact this is the unique solution due to the Brownian martingale representation theorem, which will give me the unique z. Yeah, so where do those examples appear in mathematical finance? They appear in different contexts, but the easiest here is to think of the replicating problem of eta, where eta is interpreted as a European option with maturity small t here. So if I place myself in the Black-Scholes model, the usual Black-Scholes model, the usual geometric geometric Brownian motion model, yeah. So, and if I wish to write the replicating problem for eta, I will be led to writing this, yeah, because I want a self-financing wealth process which matches exactly eta at the time small t. But when I write the self-financing condition, I will obtain something of this form with a particular form of the G, which comes from the self-financing condition, and which in the Black-Scholes model is just this, where R is the risk-free interest rate and theta is the market price of risk, the Sharpe ratio. With standard notation for the coefficients, it's mu minus R over sigma, right? So, and then if I look, for instance, if I relax a little bit, one of the assumptions in the standard Black-Scholes model, if I now allow for different interest rates, capital R for borrowing and small r for lending, with capital R greater than small r, when I write the self-financing condition and the replicating problem for the European option eta, I will find a driver, which will be this part, yeah, this part, plus the difference between the two interest rates for borrowing and lending, and then y minus z over the volatility coefficient negative part. Yeah. So in this situation, the driver is indeed non-linear in y and non-linear in z, but still Lipschitz in y and z. Yeah. So this is where those BSD become, so it's the non-linear case where they become very powerful, because they basically tell me what my self-financing wealth process should be if I'm the seller of the European option and I want to replicate it, and the Z will be closely related to my replicating strategy in the stock. Yeah. So, and now, what is this now functional? Let me explain. So this is just my pricing operator in this framework. Yeah, this is the operator which tells me what is the price of eta in my model at time s, where eta falls at time t. Yeah, and because the BSD is well defined, admits a unique solution pair. Yeah, so this operator is well defined. Yeah, this is the operator which takes as input eta and returns as output ys. Yeah, and this operator, at least in the Brownian framework, enters exactly into my my framework, and in a framework with jumps, it also enters, but I need to impose some additional assumption on G, yeah, so that to ensure the monotonicity of this operator. And let me give very quickly another example, which enters into the framework, which is a different example, where we also have dependence on the two indices, the time of evaluation S and the time when the payoff falls tau. This is the example of the dynamic concave utilities. And I can show that those dynamic concave utilities which admit this dual concave representation enter into my framework. So here is some robust representation where Q are probability measures equivalent to P, which are equal to P on Fs. And so here I have the conditional expectation of under Q, under the model Q, and here I have some penalty term on Q. Yeah, and it's in the penalty term where we have dependence on tau. So there are several colleagues who have worked on those dual representations, such as Freddy Delban, Bjorn Nadal, Rosado Janin, and Dirk Wolters. Yeah, all right. And so those are the two examples, the main two examples that I know from mathematical finance where I have dependence on the two indices and then when I'm nonlinear. And so what are my results? Very quickly, I know that I started 2 minutes late, so I still have some time to give some results. Yeah, so how is the optimal stopping problem from time zero perspective formulated? It's this one now. Yeah, so I optimize. Oh, so yeah, you understand. So it's I look at the problem from time zero perspective. If I stop at tau, I get psi tau at tau, but I want to assess that from time zero perspective so that it gives me rho zero tau of psi tau, and then I optimize over my whole set of strategies which are available to me, which are those which we call the Bermudian stopping strategies here. So I can generalize that by looking at the problem from time S perspective onwards, and when I write the problem, I get this, naturally this formulation, where theta S are of course those stopping times in theta which are greater than or equal to S. Yeah. And now, so this is my value, but of course, because I'm non-Markovian, that's not a value function, that's a value family. Yeah, for each stopping time S, I have a random variable Vs, which is Fs measurable, right? And I want to characterize this value family, and I can show so that it satisfies this dynamic programming principle. So what is this? This is really the one that you expect to see. Yeah, so here was, let's say on this, in this state of nature, this was the theta k. So I want to know what the value at theta k is. And in fact, the programming principle tells me that it's the maximum of two objects. So psi theta k, which is in fact my payoff if I stop immediately at theta k. In this framework, if I do not stop, if I miss this stopping opportunity at theta k, I can stop at theta k plus 1 or afterwards. So, but what is my value at theta k plus 1? It is v theta k plus 1, but which I have to assess from time theta k perspective. And so it's assessed by rho theta k plus 1, because it falls at theta k plus 1, but I'm at theta k. Yeah, and of course, at the maturity, the value is equal to the payoff. So, so here I have some remark about the integrability of V. Of course, I said that rho is an operator from LP to LP. Yeah, it takes LP random variables as input. So I have somehow to make some assumption on the payoff family so that to ensure that V is in LP and so that it makes sense. Yeah, so for instance, this is true if psi is dominated from above by what we call here a theta rho martingale. And so these remarks allows me to tell you what is behind this theory here. They are behind those theta rho nonlinear martingales and theta rho supermartingales. So how are they defined? So I take that a measurable sufficiently integrable M is a nonlinear theta rho martingale if it satisfies this property for all stopping times, well, of interest to me, that is Bermudian stopping times, such that S is less than or equal to tau. So in the classical linear situation, I would see here the conditional expectation knowing Fs. But here I'm not in the classical situation, so I put my rho as tau. And I write that not only for deterministic times, but for optimal stopping times. That is, I put already Dup's optional sampling theorem in the definition of my martingale. And theta rho super martingale would be with an inequality like that. And what I can show behind that is that, in fact my value family is a theta rho super martingale. And in fact, I can show that it is the minimal theta row supermartingale greater than or equal to the pair of family psi. So I can show theta row Snell envelope characterization of the value family V, which then helps me with this dynamic with establishing this dynamic programming principle. So now how about optimal stopping times in the how many seconds? In the 2 seconds which remain. Yeah, so yeah, the assumptions that we made, and in particular this left upper semi-continuity assumptions along stopping times for rho. So this allows us to show that there exists an optimal stopping time, and then the first time when V touches psi is optimal. But how do I define this first time when V touches psi in this framework? So here I look at the problem from theta k perspective onwards. So I will look at all the Bermudian stopping times greater than or equal to theta k, such that the random variable v tau is equal to psi tau. So that gives me a set of Bermudian stopping times. And then I take its essential infimum. That's also a stopping time. We can easily check that it's a Bermudian stopping time. I call it nu k. And under my assumption, this is optimal. Yeah, this nu k is optimal for the problem from theta k perspective onwards. Yeah, and what is behind here, so I will stop here. There are some technical lemmas, but what is behind, yeah, so several technical lemmas behind, but what is important to show the optimality of nu k, remember, so V is always a theta row supermartingale on the whole interval 0 capital T, but what I can manage to show with the help of the dynamic programming principle and that left upper semi-continuity is that it becomes a theta row martingale on the stochastic interval theta k nu k, where nu k is the first one. Yeah. So, and because moreover V nu k is equal to psi nu k, I can easily show that nu k is optimal. So in fact, the difficult part is showing this martingale property, yeah, nonlinear martingale property on the stochastic interval. So I have here in this framework also what I call a super martingale principle. Yeah, I call this plus something else. And this plus something else is that at nu k they touch and they equal. Yeah. All right. So I think that I can stop here. So if you look at the particular case where we have the same number of stopping opportunities, whatever the scenario, and just the timings of those stopping opportunities depend on the scenario, then you can really go by backward induction in a way that you expect. So, and we can show that this U is my V. Yeah, so I can go by backward induction. And in this case, of course, I do not need any sequential continuity properties on rho. Yeah, yeah. So, all right. So I think I can stop here. I had prepared some part 2 and part 3, but we understood already that you will re-invite me to check whether I have mastered the usage of this tool. And maybe if you indeed re-invite me, I can explain some of those problems. Yeah, we can solve from here onwards. Thank you very much.